Okay, welcome everybody. Today we are going to talk about Calc Lesson number 18, and this is the chain rule, day 3. Just to set the scene about what we have been up to so far. In day 1, it was your introduction to the chain rule and your more basic problems. In day 2, we focused on trig. Here in day 3, we're going to talk about how you use the chain rule in the context of the bigger picture of problems that need the product rule, the quotient rule, the power rule, etc. So first, a quick reminder just about what the chain rule is itself. Remember that we do have these two different notations, the first of which is the Isaac Newton notation, the second of which is the Leibniz notation. Both of those are important. Both have pros and cons. I'm sure by this point you're pretty familiar with both of them, but it never hurts to remind ourselves. Then here's a reminder of the product rule and the quotient rule. Remember, all of these rules can, of course, be found on your formula sheet, and they don't change, so continue to use them and to use them carefully. Our first question for today is to find the derivative of the following. Now, again, every single problem in today's lesson and every single problem in tonight's homework is going to involve the chain rule. What I want you to focus on is I want you to focus on what I'm going to call the big picture. When I say to you, what kind of a problem is this? The answer is never really a chain rule problem because yes, you're going to use the chain rule, but that's not the big picture. If I look carefully at its heart, this is a multiplication problem, which means that this is a product problem. So I'm going to have to use the product rule. Yes, I'm going to have to use the chain rule within the product rule, but my main focus here should be using the product rule. So I'm going to go back to my FF prime and GG prime only for the first couple if I have the, just because the first time we're really using the chain rule in the context of these harder problems, but you can continue to use this setup or not, depending on whether or not you need it. So we're going to, of course, make F the first, the derivative of which would be 2x. That's going to make our g of x 1 minus x squared to the 1/2 power. And then when I take the derivative, I have to bring down the 1/2, 1 minus x squared to the 1 less power. And then using the chain rule, I have to take the derivative of the inside, which would be negative 2x. So again, even if you haven't really been using the FF prime, GG prime notation, it might just be helpful for these first couple of chain rule problems, just to kind of get your mind right. I'm going to call my final answer here dy dx, as I've been doing the whole time. And remember that the product rule still applies. So I'm going to do the first times the derivative of the second, which is 1/2, times 1 minus x squared to the negative 1/2 times negative 2x. Another parentheses. So again, that's the first times the derivative of the second, which includes the chain rule, plus the second 1 minus x squared to the 1/2 times the derivative of the first, which is just 2x. So take a minute to make sure you understand where everything is located and what everything means. And now my main purpose from this point forward is to simplify. The truth is the calculus is over. Everything from this point forward is all about the algebra. So I'm going to go ahead and multiply through and try to simplify my first term there. So the 1/2 is going to cancel out with the 2. I see an x and an x squared, and I also see a negative. So that's going to be negative x cubed times 1 minus x squared to the negative 1/2 plus 2x times 1 minus x squared to the positive 1/2. And then something that you actually got a lot of practice on at the end of section 2.3, using all this fancy factoring, I now have to factor the greatest common factor out of each of these terms. Remember that terms are separated by pluses and minuses. So negative x cubed and 2x, I can definitely take out an x. Then taking a look at the 1 minus x squared, I have positive 1/2 of them and I have negative 1/2 of them. So when in doubt, take the largest negative out. So I'm just going to go ahead and give myself a blank screen here so I can go ahead and do that. So I am going to factor out the greatest common factor, which again is going to be x times 1 minus x squared to the negative 1/2 power. Then in terms of what I'm left with, if you look at the entire first quantity, everything was taken out except for the negative x squared. If you look at the second quantity, you took out the x, So you're left with a positive 2. Then if you look at the 1 minus x squared to the first, in order to figure out how many 1 minus x squareds you're left with, you would do the original exponent, which is positive a half, minus whatever exponent you took out, which was negative a half. That, of course, becomes a half plus a half, which is why you would be left with one quantity of 1 minus x squared. You don't have to put that exponent there, but I'm just putting it there for the moment so that we don't get confused. Just a small note here, I could have chosen to take out a negative in the beginning, but it actually turned out to be easier that I didn't. So whether you do or not, it really doesn't matter. So then continuing on, this is x times 1 minus x squared to the negative 1/2. Then inside of these brackets, this is going to be negative x squared plus 2 minus 2x squared. So from here in my brackets, that is going to give me 2 minus 3x squared. So now I am going to take my final answer and simplify it. In order to simplify my final dy dx, I'm going to leave the x in the numerator. I'm going to do 2 minus 3x squared. I'm going to take this 1 minus x squared to the negative 1/2 power, and I am going to move it to the denominator, which will, of course, make it positive. And whether I write it as a positive 1/2 power or I write it as a square root, remember, it matters not. In terms of the numerator, we normally put the higher exponent first, but sometimes we put the positive first. So again, if you had negative 3x squared plus 2, that would be perfectly fine. Again, the whole point of this problem, yes, you use the chain rule, but the chain rule was just a very small part of the bigger picture, the fact that it was a product rule problem. Keep in mind, though, if you didn't use the chain rule when you were supposed to, you would, of course, get the wrong answer. We have now seen several examples of these problems with this fancy factoring. So if you still feel like you're very lost, you should talk to your teacher sooner rather than later. But we'll get one more practice at it here in the second one. So find the derivative of the following. And again, I'm going to implore you for all these problems to look at the BP, which is big picture. So yes, you're going to use the chain rule, but really at its heart, this is a quotient rule problem. Use the chain rule where required, but focus mostly on the quotient rule. So again, I have my f prime, my g, and my g prime. So I'm going to make my f into my numerator, the derivative of which is just 1. That is going to make my denominator my g. So I'm going to rewrite that as x squared plus 4, of course, to the 1/3 power. When I take the derivative, that's 1/3 times x squared plus 4 to the negative 2/3 power, and then don't forget the chain rule. So that's why I have my 2x there. So then I left myself lots of room. I'm going to go ahead now and take the derivative. And again, because the original problem was f of x, I'm going to call my answer f prime of x. So here on the next slide, f prime of x would be equal to, you're going to start with the denominator, which is x squared plus 4 to the 1/3, times the derivative of the numerator, which is just 1, minus the numerator, which is x, times the derivative of the denominator, which is the whole thing, 1/3, times x squared plus 4 to the negative 2/3 times 2x. Don't forget that chain rule. I'm going to clean this up ever so slightly. So this is going to be x squared plus 4 to the 1/3. I'm going to drop the 1 because it's implied. 1/3 times x times 2x. That is going to give me 2/3 x squared. And then x squared plus 4 to the negative 2/3 power. So again, take a minute, make sure that I didn't drop anything, make sure you've copied everything down correctly. So now from here, you're going to go ahead and factor out, again, the greatest common factor. So if you're going to try to factor out the greatest common factor, I'm going to go ahead and change the 1 out front to a 3/3. I'm going to go ahead and want to take that fraction out. So I'm going to rewrite that as a 3/3. As I go to factoring 3/3 and 2/3, I can factor out a 1/3. This is x squared plus 4 to the positive 1/3, x squared plus 4 to the negative 2/3. I'm going to take out x squared plus 4 to the negative 2/3. As I like to say, when in doubt, take the largest negative out. So that would be negative 2/3. If you look at what you're left with from the first quantity, if you took 1/3 away from 3/3, you're left with a 3. Then you're also left with some x squared plus 4. How many? Well, you're going to do the original exponent, 1/3, minus whatever you took out. So 1/3 minus negative 2/3, which would be 3/3, which would just be 1. Maybe you're kind of catching on that a lot of times when you do this, the problem factors nicely to only have an exponent of 1. Here's the thing. If it doesn't factor nicely, there's really not much more you can do. So when in doubt, it's probably a 1. So 3 times x squared plus 4, then minus, you took out 1/3, you took out x squared plus 4 to the negative 2/3, so all you're left with is negative 2x squared. Inside of the brackets here, that's going to give me 3x squared plus 12 minus 2x squared. Clean that up a little farther. That's going to give me x squared plus 12. So right now I'm looking at 1/3 times x squared plus 4 to the negative 2/3 times x squared plus 12. Just to make it clear, if you're wondering what happened to the denominator, all of this work that I have done here is only for the numerator. My personal preference is I like to sometimes leave the denominator squared out until the final step, just because there's already enough going on. Don't forget it, but I just left it out until here. So I'm going to add it back in my next slide. Again, that is just the factoring and simplification of the numerator. Then when I get to the next slide, I'm going to bring back in the denominator squared. So right now I have 1/3 x squared plus 4 to the negative 2/3 times x squared plus 12 all over the denominator squared. Remember that the denominator was x squared plus 4 raised to the 2/3. You now have to square it. If you square x squared plus 4, that was actually to the 1/3. Sorry about that. That was x squared plus 4 to the 1/3. If you square that, you're multiplying these two numbers. So this is now going to give me 1/3 x squared plus 4 to the negative 2/3 times x squared plus 12 all over x squared plus 4 to the 2/3. So in my final answer, dy dx, it's going to be a fraction. I'm going to take this 1/3 and write it as 1/3. I'm not going to put the 1. Instead, I'm going to leave whatever's in the numerator, which in this case is going to be the x squared plus 12. This is already an x squared plus 4 to the 2/3. This is an x squared plus 4 to the negative 2/3, which means I'm going to move it to the bottom. If I move my negative 2/3 to the bottom, and I already had a 2/3, that's going to wind up giving me a total of x squared plus 4 to the 4/3. So, man, there was a lot going on there. Double check to make sure I didn't miss anything. Looks good to me. Again, you'll see that these problems are, getting more complicated the more we do of them. And the chain rule was a very, very small portion of what really is a quotient rule problem. So if you thought that the quotient rule and the product rule were gone, unfortunately, that's not the case. Here in example 3, we're being asked to find the derivative of the following. So it's the quantity 2x minus 1 over 3x plus 5 to the 7th. There are a couple of different ways that you could do this, but I'm going to show you what is the most efficient in my opinion. So again, starting with the big picture of this problem is the fact that you're using the power rule. You essentially have something raised to the 7th power. So the first thing you're going to do is use the power rule, and then you're going to proceed from there. So I'm going to, again, call this dy dx. According to the power rule, you're going to bring down the 7. You're going to raise the entire quantity, 2x minus 1 over 3x plus 5 to the 1 less power. And then I'm going to bring back that notation I showed you yesterday. You now have to take the derivative of the inside, and the derivative of the inside in this case is actually going to be the quotient rule. So that was kind of fun. You first are going to use the power rule. Now you're going to use the quotient rule. And you're, of course, going to use the chain rule if required. So this is what I have so far. Now I'm going to pop over to the side here and do the quotient rule. So doing the quotient rule means the denominator, 3x plus 5, times the derivative of the numerator, minus the numerator, times the derivative of the denominator, all over the denominator squared. And notice that I didn't use the chain rule in this step. It was here that I used the chain rule after I did the power rule. Let me go ahead and clean this up a bit. So that's going to be 6x plus 10 minus 6x minus plus 3. Remember, you have to do negative 2x times 3 and then negative 1 times 3. And that's all going to be over 3x plus 5 squared. Those 6x's are going to cancel, which means this is going to wind up being equal to 13 over 3x plus 5 squared. So this here is the result that I get when I take the derivative of the inside. So I'm going to kind of put all that together on the next screen. So the derivative started as 7 times 2x minus 1 over 3x plus 5 to the 6th. Then I had to do the derivative of the inside, which turned out to be the quotient rule, which turned out to be 13 over 3x plus 5 squared. Almost done. You're going to take that 6th power, and you're going to give 1 to the top and 1 to the bottom. You're allowed to do that as long as you don't actually try to raise each individual quantity to the 6th. Oops, sorry. So in my final answer here, man, these are good, huh? So dy dx is equal to 7 times 13 is 91, 2x minus 1 to the 6th. On the bottom, I have a total of 3x plus 5 all to the power of 8, and that is, in fact, my derivative. So far, 3 examples, 1 product, 1 quotient, and 1 power. I've got a couple more left for you. Here in number 4, find the derivative of the cosine of 5x plus 1 to the 4th. So from here, if I'm looking for the BP, which is the big picture, this is a cosine problem. That is the first thing that I'm going to focus on when I go to take the derivative. And then, of course, I'm going to use the chain rule as needed. I'm also going to bring back that notation I showed you yesterday, which, again, you can use or not. So because this is a cosine problem, the derivative of the cosine of something is the negative sign of the same something. And then you have to take the derivative of whatever the inside is. And the inside in this case would be 5x plus 1 to the 4th. So there's my first application of the chain rule. Then negative sign of 5x plus 1 to the 4th. To take the derivative of this, you're going to bring down the 4. You're going to take the entire quantity to the 1 less power. And now you have to do the chain rule again for the new inside. So negative sign of 5x plus 1 to the 4th times 4 times 5x plus 1 cubed. The derivative of 5x plus 1 is just 5. So if I very carefully simplify that, 4 times 5 times a negative, that looks like a negative 20, times the sign of the quantity, 5x plus 1 to the 4th, times 5x plus 1, that whole value cubed. So I tried to kind of set you up yesterday by letting you know that this does escalate quickly, which certainly it has. And then one last problem here for us. So the sine cubed of 4x squared, before you can think about doing anything else, you have to know that this is really the sine of 4x squared, the whole thing cubed. So in terms of the BP, the big picture, this is actually a power rule problem, because the first thing you have to do is take the derivative using the power rule, and then using your trig is what comes after. That's the opposite of what you did in the previous problem. So dy dx is equal to, bring down your 3, take the entire quantity, sine of 4x squared, to the 1 less power. Then take the derivative d dx of the inside, which would be the sine of 4x squared. So 3 times the sine of 4x squared, and then you're going to take the derivative. So the derivative of the sine of something is the positive cosine of the same something, but now you're going to have to take the derivative of the new inside. So finally, 3 times the sine of 4x squared times the cosine of 4x squared times the derivative of 4x squared, which is 8x. That is going to all combine to be 3 times 8x, that's a 24x, times the sine squared of 4x squared times the cosine of 4x squared, and that'll do it. Remember that order doesn't matter. I mean, the 24x should obviously be first, but then the order of the other two doesn't matter. And remember, whether you left the sine as the whole thing squared versus sine squared, they're equivalent, so we kind of leave that up to you. Hopefully those 5 problems will set the scene for the 7 problems that you're going to do tonight. Calc Homework 18 is 7 worksheet problems that can be found in your class notebook. So thanks for tuning in, guys, and we will catch you next time.